Why are so many people suddenly talking about computers with 128 gigabytes of unified memory? At first, that number sounds almost ridiculous. Most people are still using laptops with 16 gigabytes of memory. A fairly powerful desktop might have 32 or 64 gigabytes. So when you see a machine advertising 128 gigabytes, you might assume it is designed for professional video editing, 3D animation, or some kind of scientific workload. But there is another reason this amount of memory is becoming extremely interesting: running large AI models locally. And the important part is not only the number 128. The words unified memory are just as important today. I want to explain why 128 gigabytes of unified memory can be such a good fit for large language models, what advantages it actually gives you, and also where the limitations are, because having a huge amount of memory does not automatically turn a computer into an AI supercomputer. To understand the advantage, we first need to understand the biggest problem with running a large model locally. It is usually not storage space. You might have a 2 terabyte SSD with plenty of room for model files, but once you start using the model, those files need to be loaded into working memory. More specifically, the model needs access to extremely fast memory that the processor or GPU can read continuously while generating every single token. On a traditional desktop computer, the CPU and GPU normally have separate memory pools. The CPU uses system RAM. The graphics card uses its own video memory, usually called VRAM. For gaming, this design works very well. The game loads textures, geometry, shaders, and other graphics data into VRAM, and the GPU processes everything at very high speed. But large AI models create a different kind of problem. A model with billions of parameters can require tens of gigabytes of memory just to store its weights. A larger model can easily exceed the memory capacity of a normal consumer graphics card. For example, even after reducing a model to a lower precision format, a model in the 70 billion parameter range may still require roughly 40 to 50 gigabytes of memory, depending on the quantization method and additional overhead. That immediately creates a problem. Most consumer GPUs do not have 48 gigabytes of VRAM. Many popular graphics cards have 12, 16, 20, or 24 gigabytes. Those are already powerful GPUs, but the model simply may not fit. And when a model does not fit inside VRAM, you usually need to split it between the GPU and system memory. Some layers stay on the GPU, other layers are processed by the CPU. Data has to move between different memory pools, often through the PCI Express connection. The model may still run, but performance can fall dramatically. This is where unified memory changes the situation. In a unified memory architecture, the CPU, GPU, and other processing units can access the same large memory pool. Instead of having 64 gigabytes of system RAM over here and 24 gigabytes of GPU memory over there, you might have one shared pool of 128 gigabytes. The GPU does not need every model layer to fit inside a separate, fixed amount of VRAM. It can access the same unified memory used by the rest of the system. That means a model that would be impossible to load completely onto a normal consumer graphics card may fit inside a machine with 128 gigabytes of unified memory. This is probably the biggest reason these systems are so attractive for local AI. It is not necessarily that the GPU is faster than every high-end desktop graphics card. In many workloads, it is not. The advantage is that the GPU can work with a much larger effective memory capacity. Think of it like this. Imagine you have an extremely fast worker, but the worker has a tiny desk. Every few seconds, they need to leave the room, go to a warehouse, bring back another folder, remove the previous folder, and then continue working. That worker may be very fast, but the small desk constantly interrupts the workflow. Now imagine a slightly slower worker with an enormous desk. All the documents are already available in front of them. They can continuously work without constantly moving data in and out. Large AI models often benefit from the second situation. The ability to keep the entire model in accessible memory can be more important than having the fastest theoretical compute performance. And 128 gigabytes gives you a lot of flexibility. You could load a large quantized language model while still leaving memory available for the operating system, your AI interface, the context cache, and other applications. This extra space matters because the model weights are not the only thing using memory. As you increase the context window, the computer needs additional memory to store information about the tokens the model is processing. This is often called the key value cache, or KV cache. A short conversation might not use much extra memory, but if you load a long document, a large codebase, or a conversation with tens of thousands of tokens, memory usage can increase significantly. This is why simply checking the size of the model file is not enough. A model file might be 45 gigabytes, but that does not mean a computer with exactly 45 gigabytes of available memory can run it comfortably. You need room for the context, the software, temporary buffers, and the operating system itself. With 128 gigabytes, you have much more breathing room. This can be especially useful for developers who want to analyze large code repositories locally. Instead of sending private code to a cloud service, you can load a local coding model, give it a large amount of context, and keep the entire workflow on your own machine. The same applies to private documents, business data, research papers, personal notes, or anything else you may not want to upload to an external AI provider. Privacy is one of the strongest arguments for local AI. Once the model has been downloaded, you may be able to run it without an internet connection. Your prompts stay on your computer, your documents stay on your computer. You are not paying for every token, and you are not dependent on a remote service being available. Of course, local does not automatically mean perfectly secure. You still need to protect the computer, manage permissions, and understand what software you are installing. But for many users, keeping sensitive data inside their own hardware is still a major advantage. Unified memory can also make the software experience simpler. On a traditional system with separate CPU and GPU memory, AI applications may need to decide exactly how many model layers should be loaded onto the GPU. Load too many, and you can run out of RAM. Load too few, and the system may rely heavily on the CPU, reducing performance. With a large unified memory pool, the software has more flexibility. The model does not need to be divided across completely separate memory systems in the same way. That does not mean memory movement disappears entirely. The hardware still has caches, controllers, bandwidth limits, and different processing units. But from the application's perspective, the memory architecture is much more flexible. Another major factor is memory bandwidth. Large language model inference involves repeatedly reading huge amounts of model data. When the model generates a token, it performs calculations across many layers. The system needs to access the model weights again and again. This means performance can be limited not only by computing power, but also by how quickly the processor can read data from memory. This is why having 128 gigabytes of ordinary slow memory is not automatically the same as having 128 gigabytes of high bandwidth unified memory. Capacity determines whether the model fits. Bandwidth helps determine how quickly the model runs. For local AI, both matter. A machine with a very large memory pool, but limited bandwidth may successfully load a massive model, yet generate tokens slowly. Another machine with a smaller but much faster GPU might run a smaller model at much higher speed. So there is always a trade-off between model size, speed, power consumption, and cost. This is also why I would not say that 128 gigabytes of unified memory is the perfect solution for everyone. If you mainly run smaller models, such as models in the 7 billion or 14 billion parameter range, you may not need anywhere close to 128 gigabytes. A computer with 32 gigabytes of memory or a graphics card with a reasonable amount of VRAM may already give you a great experience. And if your goal is maximum speed, especially for AI training, a high-end NVIDIA GPU or a multi-GPU workstation may still be the better choice. Software support also matters. Many AI frameworks and optimization tools are built around CUDA, which is NVIDIA's computing platform. A unified memory system may have enough capacity to load a large model, but a CUDA-based workstation may offer better compatibility, more mature optimization tools, and faster performance for certain workloads. Training is another important distinction. Running an existing model is called inference. This is where large unified memory systems can be especially attractive. Training a large model from scratch is completely different. Training requires storing model weights, gradients, optimizer states, and intermediate activations. The memory requirements can be several times larger than inference, and the amount of computation is enormous. Even with 128 gigabytes of unified memory, you are not going to train the next frontier-scale language model on a laptop or compact desktop. You may be able to fine-tune smaller models using efficient techniques such as LoRa or CLoRa, but full-scale training is still a data center workload. So when people say a 128 gigabit e-machine is good for large models, they usually mean running quantized models locally, experimenting with them, building applications around them, or performing lightweight fine-tuning. Quantization is a key part of this story. Large models are normally trained using relatively high-precision numerical formats, but for local inference, we can reduce the precision of the model weights. Instead of storing every parameter using 16 bits, we might store it using 8 bits, 6 bits, 5 bits, or even 4 bits. This can dramatically reduce memory usage. A model that would normally require well over 100 gigabytes might fit into 50 or 60 gigabytes after quantization. There can be some loss of quality, especially with more aggressive quantization, but modern quantization methods can preserve surprisingly strong performance. This combination is what makes 128 gigabytes so useful. The unified memory provides the large shared space, while quantization allows models with tens of billions, or sometimes more than 100 billion, parameters to fit inside that space. You can experiment with different quantization levels, context sizes, and model architectures without immediately hitting a hard RAM limit. And I think that is the real appeal. It gives individual developers access to models that previously required expensive servers or multiple graphics cards, not necessarily at data center speed, but at a level that is practical enough for experimentation, research, coding, document analysis, and private AI assistance. It also changes the way we think about buying a computer. For years, most people focused on CPU cores, GPU performance, and SSD capacity. But in the local AI era, memory capacity and memory bandwidth are becoming just as important. A machine may have a powerful processor, but if it only has 16 gigabytes of memory, the range of models it can run will be limited. And unlike storage, memory often cannot be expanded easily on systems using integrated unified memory. That means choosing 64 or 128 gigabytes at the time of purchase may determine what kinds of AI models the machine can run several years later. Personally, I see 128 gigabytes of unified memory as a kind of sweet spot for serious local AI experimentation. It is large enough to run models that are far beyond the typical small local chatbot, but it is still available in machines that can sit on a normal desk without requiring a server rack, industrial cooling, or multiple power-hungry GPUs. You get a quiet system, relatively low power consumption, and access to a large shared memory pool. But I would still choose based on the actual workload. If I only wanted fast responses from small models, I would probably prioritize GPU speed. If I wanted to train models or use software that depends heavily on CUDA, I would choose an NVIDIA-based system. But if my main goal were loading very large quantized models, working with long context windows, and keeping everything local, then 128 gigabytes of unified memory would be extremely attractive. So the answer is not simply that more memory is always better. The real advantage is that unified memory removes one of the biggest barriers in local AI, the fixed VRAM limit of a traditional graphics card. It allows the CPU and GPU to work from one large pool, reduces the need to constantly divide the model between different memory systems, and gives large models enough space for their weights, context, and runtime overhead. It will not give you unlimited speed. It will not replace an AI data center, and it will not magically make every model run perfectly, but it can allow one compact computer to load and run models that would otherwise require much more complicated and expensive hardware. And that is why, as large language models continue to grow, 128 gigabytes of unified memory is becoming one of the most interesting hardware configurations for local AI.